reputation is math more than just numbers. Since 2000, the Organization for Economic Cooperation and Development, OECD, has conducted the Program for International Student Assessment Test, or the PISA test. This test aims to quantify mathematical proficiency in 15-year-olds in 65 various nations. Here are the results from the test for 2012. I know this may be hard to see in the back, but let me highlight a few things. First of all, you'll notice that China is number one, specifically Shanghai, China, but Asia makes up the top 4 or 5 of the list. Second, we'll list the last, Peru, and then we'll get to something a little closer to home, the United States, which ended up 36th on the list, nestled between Lithuania and Slovakia. So a slightly different angle compared to GDP. So on the left, you have the highest ranking country, and on the right, you have the lowest ranking country. And the bars represent the GDP of the country, which is a good gross domestic product of the country, which is a good estimator of the size, the development of the country. So as you can see, it's a little disturbing that the most developed country, the United States, with the highest GDP, is in the lower half of the countries. And then one final list, or graph, just showing the history of the ranking of the PISA test for the United States over the course of the test over the past 5 tests. So as you can see, this is not a new problem. We've consistently slipped over the past 5 tests. So how do we stop this trend from continuing is the main focus of my project. To begin, I had to learn more about, I didn't have to learn more about that. 1 second. There we go. To begin, I had to learn more about higher level mathematics. I enrolled in a course entitled Introduction to Mathematical Thinking through Stanford's online high school program. The goal of this course was to teach how to think mathematically and to solve real world problems. To give an analogy, most high school mathematics is like learning to drive a car. You learn how to do something fairly simple and repeat it again until proficiency. College mathematics, on the other hand, teaches how a car works. It teaches how to maintain and repair it, and potentially how to design and build your own car. While learning to drive the car is necessary, these additional capabilities provide far greater opportunities for application in the real world. This mathematical thinking was taught through mathematical proofs largely. Proofs are essentially the how and why that fall behind every mathematical concept. The study of these proofs gave me an idea. What if high schoolers could gain access to these proofs? What if, instead of just learning that certain properties in math exist, people could start to understand why those properties exist in math? The challenge I faced was the complexity of many of these college-level proofs, as they were intended for an upper-level mathematics audience, mostly PhD students. Now, I'm sure many of you cringed when you first saw this proof. This is a proof that the sum of n odd integers is equivalent to n squared. This proof utilizes a technique known as induction, which is fairly common in the world of college-level mathematical proofs. Induction utilizes 2 main steps. In the first step, known as the base case, a particular property is demonstrated, usually for the smallest natural number, 1, but it can vary depending on the circumstances. In the second step, known as the inductive step, it is proven that a given property exists for one particular case, and then that proves that every case after that is proven by that case. It sort of creates a domino effect where the previous case always proves the next case, and so you can assume it for all cases. So, enough of that. An alternate representation, a little more colorful, a little simpler to understand. Utilizing the saying, a picture is worth 1,000 words, I have transformed the proof from the previous slide into a much more simple visualization. Each color representation is an odd integer. Blue represents 1 with its single dot, red represents 3 with its 3 dots, and so on. The proof makes it evident that the sum of n odd integers is indeed going to be equivalent to n squared. For instance, take the first 3 odd integers. 1 plus 3 plus 5 is equivalent to 9, which is also equivalent to 3 squared, or 9 as well. The idea that college-level mathematical proofs can be simplified using visualization is the main idea that fueled my project. One more, slightly more difficult, but perhaps a little bit more familiar proof, the proof of the Pythagorean theorem. To start the proof, we take the tilted square with side length c. So the area of the square is equivalent to c squared. This square is then divided up into 4 right triangles, as shown. The short leg of each of these 4 right triangles is labeled A, and the longer leg is labeled B. We then rearranged the triangles by taking the blue triangle in the upper right and moving it down to the lower left, and the red triangle in the opposite direction, giving us a shape that looks like this. When we look at this compared to our previous shape, we'll note that the smaller square is actually equivalent to, both of its sides are A, so it's a square of side A. And the larger square is a square with equal sides, equivalent to B. So with a little bit more simplification, we can say that C squared, the initial volume, is equivalent to the smaller square, A squared, plus the larger square, B squared. Hence the Pythagorean theorem. So I set out to write a book of simplified college-level math proofs. To aid in this endeavor, I enlisted the help of 4 colleagues from my Stanford math class, including 1 student from Shanghai, China, 1 from Delhi, India, and I also gained the assistance of a PhD student from Stanford, pictured here, who had invaluable experience in writing similar math textbooks. To construct the textbook, I used LaTeX, which is a typesetting language which allowed me greater manipulation of the proofs and their visualizations, respectively. My responsibility in the group was to coordinate my colleagues' efforts and write my own math proofs. We had weekly meetings via Skype to discuss plans and any issues we might have with particular proofs, of which there were many. So I apologize. After around 16 months, we have successfully completed a sample of our proofs. This sample included 6 particular proofs that were more well-developed than the others we have in our book currently. They were from areas such as general truths, hitting on topics such as the square root of 2 is irrational, and one other one. I apologize. And then the second topic was on triangles. We hit the Pythagorean theorem from the previous slide, and we also hit a property that you guys have probably learned about in math class, that the limit as x approaches 0 of sine of x over x is equivalent to 1, which is very useful in trigonometry. And then the final, we hit calculus with 2 main proofs, the mean value theorem and the integral test, which, if you haven't learned already, are pretty essential to calculus, so that was good. To evaluate the effectiveness of this proof, I conducted a literature review. To conduct this literature review, I distributed the sample to 3 teachers, seeking their feedback in 4 main areas. Was the proof clear? Were the illustrations neat? Was it interesting to read? Because no one's going to pick it up if it's not interesting. And was the proof significant to the area of study? Because there has to be some application. The literature review showed me that we still have a long way to go, but we're on the right track. In general, the formatting and significance of the proofs were not an issue. However, I did learn that it is extremely difficult to explain math in a concise and clear manner, because everyone has different experiences and different knowledges when it comes to math. So, and I think that I'm not completely at fault here, given some of the things written in our own math textbooks at school. It's very difficult to explain. While from behind my computer screen I thought that everything was described well in many cases, the review brought to my attention things that I had overlooked, steps that I had overlooked in the proofs. In addition, a couple of teachers identified that one of the proofs was actually not a proof at all, but rather a demonstration, which they're very similar, but the demonstration doesn't quite emphasize how the relationship exists. It's more just a demonstration of that it exists, which is what I was trying to get away from. Additionally, in discussion with my group, I found that this style of proof has some scalability issues. Not all proofs can be represented visually, but thinking about my initial target audience, I wasn't intending to scale all or change all proofs into a visual representation, rather just a few that could enhance the high school atmosphere. So this con can largely be negated. However, despite these shortcomings, my overall goal was achieved. These visual proofs were simpler than their traditional counterparts. So overall, the pros of this project far outweighed the cons. One of the few drawbacks I did run into was that it was very time-consuming. Especially being a newbie to LaTeX, it was very difficult to learn how to do certain things, like write certain formulas in a certain way or visualize things with a graph. So I had many experiences where it didn't print out exactly what I was anticipating. As for the pros, detailed research was required to construct each of the proofs, so I did learn quite a bit of new math in the process, which I see as a pro. In addition, coordinating individuals from around the globe gave me a good deal of leadership experience. We only had email to communicate with one another and Skype every week, So it was difficult to make sure everyone was on the same page in a thorough manner. It's a lot easier when you're face-to-face. In addition, we had different time zones. Shanghai is about 12 hours different from us, so that was tricky coordinating. And we were all fairly busy students, so schedules were difficult to coordinate. Finally, through the course of this project, I gained proficiency with a new typesetting language, LaTeX, which will most likely be a welcome asset in college whenever I'm doing math and science-related things. So to conclude my presentation, I'd like to thank the following individuals. Ms. Graves for dealing with me and pointing me in the right direction when I ran into difficulties. Ms. Letts, Ms. Anderson, and Mr. Dolmage for actually doing the review of my proof and giving me invaluable feedback. Arya Rodley, Stravia Vamanapati, Yikong Shen, and Gilan So, who were my collaborators and gave me great insight into things that I was having trouble with. Philip Wong for mentoring, inspiring, and encouraging me. And all of you for attending my presentation. Thank you.